Good day, dear ones. Today we will be exploring about the DC missions. This is an introductory lab. It's not a difficult lab, but just it is the first part of DC missions. Uh, this lab is just we made it a preliminary one, but the next lab is the actual DC missions lab, DC motors lab, where you will be studying the speed control and characteristics of the missions. Just today, this one is just introductory lab. Okay, so that's why we added some few things like knowing about the prime mover, uh, dynamometer, and then DC missions, and then we'll be just measuring the resistance of armature winding and field winding and series field winding. So these are the simple objectives in my opinion, and I'll be using this data and report template to record the data for you for the report. Okay, so the first one is the prime mover operation we will be studying. Okay, first step is the setting up this circuit. Okay, this first time directly we are setting circuit in that case. So look at the circuit diagram shown in figure 1.0. So this is the circuit diagram we will be connecting, I guess. So if we observe this circuit diagram, you can see it's very simple in nature. So we have a variable power supply and 7 and N terminals we'll be using. This is the variable power supply, and we'll be using the prime mover, which has only two terminals. One is terminal 1 and 2, and you'll be applying voltage, and we'll be monitoring the voltage by using E1. And this prime mover will give the speed output, torque output. So those signals can be transferred to the DAI, data acquisition interface, where we can see the values of torque and speed on the lab world software kind of thing. So in the metering window, you can see those values. So okay, so you might wonder that how come this prime mover is just having only one winding. So I think this winding is the primary armature winding would be, and the field winding to get the flux, it may be deriving either from this one internally, or there is a permanent magnet is there to produce the flux. So when you have a flux, and then if current is flowing through this through the flux through the conductor which is placed on in the magnetic field, it will produce the um, torque. So basically the prime mover is used uh, as a source for mechanical energy to the electrical machine. So the electrical machine, if you use as a generator, the electrical generator function is to convert the uh, mechanical energy into electrical energy. So that mechanical energy we have to in real world, it can be a turbine, like a hydro turbine or wind turbine, or a steam turbine, or different in the nuclear there is a steam turbine is there. Yeah, so the water gets heated and vaporized, and then the steam can be used. So different kinds of mechanical turbines would be there. Those would be providing mechanical energy to the giant generators in the field. But here in the laboratory things, so those things we can't mimic here. So that's why we would be using the prime mover to rotate the electrical machine as a generator kind of thing. So that means simply when you remember prime mover is, if the moment prime mover comes to your mind, that means it will be providing a mechanical energy to some electrical generator kind of thing. That is the simple thing. And how it works and all kinds of stuff we will be uh, working here, I guess. So I think we looked at the circuit diagram here and identify the modules and terminals that are to be used in the circuit. So I will show in a moment what are the modules we'll be using. So we'll be using the prime mover module and power supply module and all kinds, DAI, all kinds, and the terminals will be identifying, and then determine the colors. We have black and red color there, so those are the colors we'll be using. And remember, the dotted line represents the white color wire. If you see here, so this is the dotted line. It is mentioned it's a common wire. It's a reference wire. So these two signals are referenced with respect to this one. So like a neutral for this one, maybe kind of thing. So, and then we'll set up the circuits without overhanging using appropriate length of wires. No unconnected wires to be on the table. That is generally for tidiness and everything. This kind of instruction is there. But let me quickly show you, shift the camera, and then we'll wire this circuit. Okay. So this is the station. You can see here. This is the power supply, and we'll be using the variable DC power supply 7 and N, and then this one is the prime mover here. So this prime mover has got here, you can see the prime mover input here. So these are the two terminals, 1 and 2 terminals we will be using here. We'll be using these two terminals, and in the DI used before, and you'll be using the voltmeter 1 volt. That's the terminals you can identify. So let me connect the circuit for you. It's very simple in my opinion. So I always start from the power supply. Always the higher potential terminal or positive power supply. So we'll start from 7 to 1 it will go. So I will take a medium wire. I think it will fit medium wire. So because I'm using color coded wire, so red terminal automatically my hand will go there, and then black terminal, I think will it fit? Let me check. Yeah, it won't fit. So I will use the little longer wires. So that is the one I will be using. Okay. So that is the connection. So these are the connections. So this one I connected here, and this one is connected here. So I generally start from power supply, goes to this prime mover, and then comes back there. And the voltmeter will be connecting across this to measure the voltage. So I will take a red one. So let us see if this one will reach. Not reach. This also will reach. So I will use the medium length wires. Okay, that's good. So since I'm using color code blindly, I can connect the black one here and red one here. So the black goes there, and then red goes there and the black goes here. So that is the voltmeter connection. And for this one, so I'll be using a control cable, because these wires they cannot. So if I notice the speed output and speed torque output here, and you can see these are the small different wires we have to connect. This one we cannot put it there, so that's why we have different wires here, control cables we call. So if you see this control cable box, each station would be having a box like this somewhere on the top of the station, somewhere it's located, and then there is a red trim color, yellow color, and then there is a white color there. So these are the three wires I'll be using. I think in this circuit diagram the power supply to the DAI is not mentioned, so definitely this is the wire it to be connected, so that also I need to use it. So okay, maybe it in instructions is mentioned but not in the diagram, so we'll figure out. So because this prime mover needs its own power supply, it should be coming from here, so maybe we'll use it later, but right now I'll connect according to this circuit diagram. Torque is yellow, connect here, T for torque, and the speed output is speed we measuring we designate a symbol N, N for speed, and the common terminal. If you see these, there are three terminals are there. They are all common terminals. Anywhere you can connect it here. But if you see here, there is only one common terminal for this one. So I'll just connect that one. So this is the circuit diagram. It's very simple in nature. So let me go back to the instructions and see what is the next one. So the next instruction is to access the LabVolt software. So make sure the low power cable, gray cable coming from the DI is connected to the jack of the control power supply and the main power supply switch. I think let me show you quickly what is that, these two instructions, and then on the power supply 24 volts power switch red should be on position, LED and DI should be on. So these two instructions quickly I will show you on the and at the field. So this is the power supply, and this is the gray cable it's talking about. This one is be connected to the DI. So the other end is permanently connected and this end is not connected. You can replace when you want to move the modules for service or for some reason. So one side should be flexible. That is the reason it is not permanently connected. The other end is permanently connected inside. And if you see, that is the red switch. This is the control power supply, 24 volts control power supply. If I turn it on, you would see LED, green LED will lit there. So that is the one. Before we open the LabVolt software, that is the requirement to power on the DI so that you can communicate with the computer. So the next instruction is we need to look for LabVolt software. So we can search with letters LVD, something like that. So if I go to the search field here, so if I press LV, then automatically that LV DAM EMS system comes. So if I click here, it will open the software, and you can see a click sound. I don't know whether you could notice or not. There was a click sound. That means the software is communicating with the DI in the physical world. So then what else we need is, and then this instruction is only for new DI, so we are not using the new DI, just ignore that one. Okay, and on the main window toolbar, so this is the main window. It's these are the toolbar. Here you can see different instruments are there here. If I place your cursor on that one, it will display what it is kind of. This is the metering window, that's the oscilloscope, and this is the phasor analyzer. You already know about this one. And then on the metering window, activate meter E1, T and speed. Since we need input voltage, so we'll just open this window, and then just generally I click this continuous refresh button to see if it is communicating it properly or not. If it is not communicating, it would show 120 volts there. That means there is something wrong with the things that I can take a corrective action. So it's already E1 is activated, so I can deactivate the other meters to avoid confusion. And then there is a T, meter T for torque measurement, and this is the N. This is the meter N for the speed measurement kind of thing. Right now they are giving some stray values, that means unwanted or noise we call. Actually it's electrical noise, not the mechanical noise like sound kind of thing. So that is the value. So if you see here, this NC button is there here. If you, that NC means it's not corrected or no correction, something like that. So what does it mean? Means whatever the value displayed on the prime mover, it would be directly displayed here. Suppose it's showing 0.3 there, it should be 0.3 here also. And there is a one function here. This is the like the corrected value. The corrected value I will explain when the time comes, but right now, so it's not corrected. We don't need any correction kind of thing. So we'll leave it there. Okay. And then what is the, oh, it says the meter T, make sure you see NC. So we see NC there, that is the thing. And the NC means not corrected. Change the meter type for meter E1 to DC by clicking on AC button. Okay, so this meter by default it will measure the AC quantity. It's AC RMS value, so that's why it's AC type. And then if because we are applying DC voltage, which we should measure the what is it, average value. So that will click here, because anyway in DC, if it is pure DC, the RMS and the average value should be same. That is the DC type, but we will be selecting DC here. Okay, and then deactivate all other meters. I already deactivated. Run the application by clicking continuous refresh button. I did it at the beginning itself. And I think it is asking to open the data table to record the things. I think what I will do, I will copy the window, or maybe that is okay, let me follow the instructions. So this is the meter data table here, and if you see the options here and record settings, since our metering window is open, so it will by default select the metering window, and whatever the meters active, they are already selected. So if you click here, it will try to record the voltage, torque and speed kind of thing. So if I change it, will it CNC, and no, it's not showing anything. Okay, that is, we'll just separate it to avoid overlap. Okay, so, and then I think it's asking to figure out the record setting. Record settings I already did. Okay, and physically checking the equipment. Physically check the equipment listed in table 1.3. Yeah, not so. This one should be done at the beginning, I guess. it's showing right now. So we need the prime mover and then DC motor there, so we already have it. I checked it. And then timing belt, make sure the timing belt is not connected. So the timing belt should not be connected, so I already made sure it's not connected there. That's good. So I will show in a moment when I turn the camera to the equipment. And the control cable to prime mover, so locate the control cable box, usually located on the top of the station. I think this should be also given somewhere. The sequence is a little bit weird here, but anyway, we know what is that cable. I was talking about this cable I showed you before. So this is the cable it's talking about. So we'll be connecting that one gray cable, connect between low power input jacket of the DI and prime mover. So only one is enough. Sometimes there are two jacks there. Sometimes students they try to connect two. It's not required. That's why this instruction is given. And the power supply, make sure the voltage control knob is at 0 and the main power switch is 0. This is the safety instructions, that's why it is given there. And in the prime mover dynamometer control settings, we'll make some mode switch should be in the prime mover. Since the machine can be used as either prime mover or dynamometer, there is a mode switch, which mode you want to do, whether you want to have prime mover mode or dynamometer mode. That is the mode means the way how you wanted to use it kind of thing. So prime mover will be using. And then there is a display switch. It can either measure the speed or torque. So we'll select the speed for the time being, and then we'll get the things verified. So since you are not here, I self check myself, and then we'll turn on the power, and operating the main switch, and applying voltage to match the speed. There is a problem with speed matching with some stations, so this is the instructions made available. So what it does, generally when we apply some voltage, the prime mover will show some value, but the metering window in the lab volt will show different value. It may be 50, 100 RPM difference kind of. Sometimes it's 10 RPM. If it is 10 RPM kind of thing, we just ignore the change and then we'll record it. But if it is too much variation, 30, 40, 50 kind of thing, then we will take the value from the prime mover as a correct value and then record it. So to correct it, with experience we found that if we go to 100% and then come back to 0, so at some point somehow the electronics got reset or something happens, then the speed gets corrected. That's why the step is there. And then so we'll basically apply 50% of the position. Will turn on the voltage control knob to 50% and then see what is going on kind of thing, I guess. That's why the record button is there. So I will just do these steps for you, and then we'll do the experiment. Okay, let me turn the camera to the field. So this is the thing here, and this cable will be first connect this one here. So between the DAI and the prime mover here, you can see that the LED is on, and you can see the display here. So in the prime mover dynamometer module, there some settings we have to make. Since we are using it as a prime mover, so the mode switch, this is the mode switch, we have to turn into prime mover mode. So in the dynamometer mode, what happens dynamometer? So when the machine is used as a mechanical load to the electrical machine, so the dynamometer mode is used where to apply a torque by using this control layer here. So in that case, what happens? It doesn't need electrical energy; it needs mechanical energy. That means so the belt should be connected, and then mechanical energy coming to this one, and that when we adjust this one, the load can be controlled, kind of thing. So electrical input will be cut off when it is in the dynamometer position. There may be a question about this. This one just I'm giving a hint there. Okay. And this display switch will measure the speed and torque. So right now we'll measure the speed, so that's why it's in the speed position there. So we no need to worry about this one. This is the when we are using dynamometer, so these settings we have to worry, so we no need to worry about that one. And it was also mentioned about the timing belt. This is the DC motor generator here. This is the prime mover. Between these two, if you want to couple them, you will be using the timing belt. So the timing belt is generally hidden here inside the prime mover. So that one would be connected. So it right now it should not be connected. That's why. So I made sure it is not connected. It's there. Let us keep it here. Good. So that is the things. Think then we will go to. So power supply. We will make sure it is at the voltage control knob is at 0 position, and the switch is at 0 position also to the safety. That means if you by mistake if it is at 100% and if the wiring is wrong, and the moment you turn on, high voltage will be applied to the wrong circuit, it may destroy the things. So that is the reason that thing is there. And then verification I already did, it's a very simple thing. And then powering up, so we'll be turning on the power. And then so this instruction is for the speed matching instruction here. So right now it's showing 0.03 something like that. It's showing 0 there. That is fine. So let me apply a little voltage and see what is going on. Okay, I forgot to switch to prime mover position. So now let us see. I just arbitrarily applied some 20%. Let us apply 20%. So it is showing 510 RPM there, and here it is showing 512 RPM. That is very good. That's a good thing. It's very close. So, but for some stations the difference would be very high. So in that case, what we would be doing? So we'll be going to maximum like this, and then coming back to 0. That way the speed would be corrected, kind of thing. So luckily we no need to do this one here, but still we will just go through this process if there is any something like that. So, and then we are asked to apply, I think, 50% of the things and record these things. So at 50%, this is the 50% position there. It's showing here 1320 here, 1320, and it's showing 1327 RPM. That is very close. So we will take the readings there. So it is showing negative 0.174. So when we have that positive speed, the torque, the symbol indicates it's opposing torque kind of thing. That is the reason that negative symbol is there, and we apply positive voltage. There is a positive voltage we apply. The positive voltage we apply, so speed will be in positive. That means it is rotating in the clockwise direction, and but the torque produced inside would be in opposing in the moment of the rotation. That's why it's negative symbol is there. So I will just record it by clicking this record button here. I think this one I can delete it, so that way should be recording there. So let me what is the next step? I think that is the recording. Record the data, and then it should be turning off the turn the power to 0. Okay. So since I recorded the values, I will just copy this one. Where is that one? So I will use the snipping tool to record the value, and then I will place. So this is the from the previous experiment I am using. So just delete it, and then I will place it. If I save it, I think the word is not crashed. That's very good symbol. Then record the direction of rotation. The direction of rotation, I think I can show you if you observe the here by applying little voltage. You can see here. You can see that there is a hole there, and that hole is rotating there on the spindle, the pulley kind of thing. So you can see it's a clockwise movement is there. So rotation is clockwise. Clockwise rotation is there. That is what I will record it and save it. So what is the next one? And reverse the connections as shown figure. So we will reverse the connections at here. So that means initially the red wire is connected to the terminal number 1 here, but now it's reversed. So we will be reversing here in this circuit diagram. The same circuit diagram, only thing is we will be just so here black is connected to the 2, and red is connected to the 1 here, and we will just reverse the connections here. Here I think when we reversing these connections here,